All right, so let's go ahead and let's get started with the last instantiation of our tutorial series, which will be on ALTRO and TrajectoryOptimization.jl, which has been developed by myself. So my name is Brian Jackson. I've been working with Dr. Manchester for the last 4 years, so I'm just starting the fifth year of my PhD. I am at Carnegie Mellon University. I started my PhD back at Stanford with Dr. Manchester and just transferred to CMU last year. And a lot of my research has been focused around developing the tools that we'll be going over today, namely the ALTRO solver, which stands for Augmented Lagrangian Trajectory Optimizer, and then its associated packages. So we're just going to start off with a very high level description of kind of what the solver is, what its goals are. We'll be working kind of basically directly off of the tutorial website that was launched just about last week, and going through some of the documentation, and then we'll actually just going to launch in with some live code demonstrations that will hopefully all work out perfectly smooth. So if you want to know where this is located, if you come over here to the NPC website, so this is just the workshop website, come all the way down to solvers, and there's a link to the tutorial here. And we'll be sure to update the descriptions here with additional links for the other tutorials by the end of today or tomorrow. So what is ALTRO and TrajectoryOptimization.jl? So they are essentially an ecosystem of packages developed in the Julia programming language for setting up and solving constrained nonlinear trajectory optimization problems. So already had some amazing work presented by the previous two solvers. So I don't think we need to go over too much of the theory. But do want to quickly clarify the type of optimization problem that we're looking at here. So as this should look very familiar to the versions presented by the previous two workshops, where we have some nonlinear cost function that's Markovian in that there's no coupling between kind of adjacent time steps. And then we have some generic nonlinear dynamics. Here we're going to kind of basically assume that we've already discretized the problem. Like Nicholas mentioned at the beginning, the problem of transcribing your continuous time problem into a discrete one is very important. But here we're going to assume that that process has mostly already been done. So what we can do, and what this package does allow you to do, is define your continuous time dynamics and then apply some standard integrator like Euler or RK3 or RK4. So those are implemented for you. Other than that, it's kind of on you to more or less define how you want to set up a discrete problem of this form. On top of that, we can add additional equality constraints. Again, these can be generic nonlinear equality constraints that potentially couple both the states and the controls at each time step independently. And then I guess what sets ALTRO apart from the other two solvers that we've seen today is that we can handle generalized inequalities. So right now we can handle generic, just normal inequalities, but we can also handle with respect to the second order cone, with future cones coming in the future. So what this allows us to do is handle things like the full friction cone or things like the rocket soft landing problems. We have examples of those in the tutorial Jupyter notebooks that we put together if you want to check those out. And it does, as far as the 10,000 foot view of the ecosystem, I'm just going to kind of refer to it as the TrajectoryOptimization.jl ecosystem, because that's really was the original package, which we then kind of split into three kind of core packages, which are listed down below. But as far as the entire ecosystem goes, the key features here, or I guess the key design goal here is slightly different than the other two solvers, which were written in C++. The design here was really to kind of be a go-to a place for developing novel algorithms for research. And so we're using a high-level programming language called Julia, which has syntax very similar to Python or MATLAB. So it makes kind of developing these algorithms very fast. And unlike Python and MATLAB, it uses it's very, very fast. So it uses the same compiler underneath that Clang and Rust use. So the final code ends up being very performant, and we have performance on par with C++ implementations. But this kind of the way that we've set it up in this high-level programming language allows us to iterate very quickly, try out new ideas, and hopefully allow the community to do that as well. So we provide a very easy, what we believe to be like very intuitive API for setting up, solving, and analyzing the trajectory optimization problems that you get out. In general, we're focused on single-stage nonlinear trajectory optimization problems. So right now we don't have kind of built-in support for switch systems or locomotion problems. It's really kind of focused on either like single rigid bodies or things that you have well-known analytical dynamics for. So we also provide methods for natively accounting for the group structure of 3D rotations. And then we also, similar to Farbaude's OCS2, we provide automatic differentiation using forward mode automatic differentiation or finite differencing through some very like state-of-the-art and mature Julia packages for doing that. And then one of the other great things about working in Julia is that it interfaces super well with other optimization solvers. Pretty much every optimization solver out there is wrapped in Julia. It has a very, very kind of robust and active optimization community. And there's, so you can easily compare to a lot of other solvers. Just literally you go to the command line, type like add IPOpt, it'll download the binaries for your computer and then set up the wrapper and you're off to go in like less than a minute. So it's, it definitely has some nice advantages. So as far as the core packages go, we have robotdynamics.jl, which takes care of kind of defining your dynamics. And then we have TrajectoryOptimization.jl, which sets up, it's essentially the front end, as Nicholas said. This is the domain-specific language of setting up and defining the problem that you're trying to solve, adding constraints, defining a discretization. And then we can pass off that problem definition to the ALTRO.jl solver or the backend to actually solve and compute the optimal solution. We also have some additional packages that we'll be using in the examples. So RobotZoo just holds a bunch of different dynamical models, anything like from the canonical Cartpole or pendulum to, I think we have a linearized quadruped model in there and like a planar rocket. So I think we have about 12 to 15 different models in there that you can very easily go ahead and just use to get started on your problem. And then we also have a plotting library that supports both 2D and three-dimensional visualization for all of the models in RobotZoo. And as far as, I guess I can come back to this at the end as far as the future direction, where we're headed at the end. But as far as installation, you can just go ahead and install Julia. It's super easy. You basically just like download the binaries, put it on your system path, and you're ready to go. And then I'll actually show you how easy it is to install ALTRO. Oops, let me terminal. All right. So if I have Julia installed, I just come over here, I hit this right square bracket, and I type add ALTRO. And it'll download the latest version. And I already have it installed, so no problem. This usually takes maybe like a couple minutes to install at most. And I can check to see if it's installed using the status command. And I can see here I have the latest version of ALTRO. And also I have trajectory optimization and the other packages installed as well, which I've already done that previously. So just a quick note, when I type the add ALTRO, it'll install all the packages, but you won't be able to explicitly use them until you also type in like add trajectory optimization. So for those of you who are new to Julia, the package manager is really nice. It's one of the reasons we love it. And it helps you get started very quickly. Okay, so now let's actually start with some examples. I guess before I start with any examples, I'm just opening up quickly for any questions that you guys have about kind of the high level goal of trajectory optimization or the algorithms that are being used. Feel free to just raise your hand or put some questions in the chat box. All right, so if nobody has any questions, we're just going to go ahead and start off on some of the examples. So these are in the, if we go over here to the examples, these are all have links down here. I've set up about 5 different examples that kind of walk you through varying like advanced features to simple features. They more or less go in order, and you can see kind of the the ideas or the concepts that are being introduced in each one of those examples. So we're actually going to start with the second one, just for sake of time. And we're just going to walk through it, and hopefully you'll get a good feel for how to use TrajectoryOptimization.jl, kind of what its capabilities are, and how potentially you could use it in your research or on your problems. So to start off, we're just going to pull in or import all of the packages that we want to use. So here we're going to pull in ALTRO, trajectory optimization, robot dynamics, and then some additional packages as well. I guess one quick note that you'll notice that it takes a little bit of time the first time you'll evaluate everything, because Julia is it's not pre-compiled, it's just in time compiled or JITted, meaning the first time you run everything, it'll take a little bit of time. After you take that, it'll compile down to some native code on your computer, and it runs super, super fast. So just something to be aware of if you haven't used Julia before. So the first step that we're going to do is we're going to add or define our dynamics model. So very similar to kind of what Farbod mentioned with his package, we have some abstract like interface class that we want to kind of define our own functions on top of. So in Julia, this looks like this, where you're just going to define your own structure. We're going to call it Cartpole, and it's going to essentially inherit from the abstract model that lives in robot dynamics. And here we're just going to define the mass of our cart, mass of our pole, length, gravity. We can add all those parameters that we want. And then we just instantiate, or we define a new dynamics function for our Cartpole. So here, this is just specifying that this is for this particular model. We're taking in our state and our control. We define that as follows. I'm not going to spend any time on kind of deriving that or anything. Hopefully everyone knows how to derive a Cartpole. And then the only other thing that we need to do is define the state and the control dimensions for our model, and we're ready to go. So robot dynamics will automatically do automatic differentiation for you to define your Jacobians for the state and the control. And then for our cost function, pretty much all the cost functions we're going to use today are just going to be basic quadratic ones that we've already seen. We're just going to create our model, pull out our state and control dimensions. We're going to pick 100 knot points, a time horizon of 5 seconds. And we're going to use some of that information to define our cost. So we're just going to use a regular quadratic tracking objective with quadratic weights. And we're going to penalize the distance from our final state. So we can do that using the convenient ALQR objective, where we pass in all that information along with the number of knot points. And this will create a bunch of basically 101 different cost functions that are all kind of collected together into one structure that we call the objective. All right, and then now that we have the dynamics and the cost function defined in just maybe 10 like 20 lines of code, we can go ahead and start adding constraints. So ALTRO handles general types of constraints like we saw before, and so there's the process for adding those to your problem is very straightforward. All you do is you start up with you create a constraint list where you pass it the state and the control dimension, and then the time horizon. It's really just to allow it to kind of do some cross-checking to make sure that the sizes for the constraints that you're defining are consistent with what it expects. All right, so we're going to go ahead and create our constraint list, and then we're going to define our constraint objects. So these objects are going to be responsible for evaluating the actual constraint as well as its Jacobians and its derivatives. So here we're just going to create a bound constraint and a goal constraint. So now that we've defined those objects, we now need to tell it where on the trajectory we're going to apply those constraints. And we do that just by adding the constraint to the constraint set and telling it which knot point indices or time steps that we want to apply it. So here we're going to apply the bound constraint for our Cartpole on all from time steps 1 to the penultimate one where we have all of our controls. And then we're going to add the goal constraint to our terminal time step. As a quick note here, kind of like what Farbod mentioned, we assume that the constraint Jacobian that you get out is going to be full rank. So if you get any weird error messages saying like indices out of bounds, as usually due to this. Say, for example, I have a state constraint that's like keeping me off the floor, and then I also apply a goal constraint. Those two constraints are going to be redundant, and I'm going to no longer satisfy the full rank condition, and the solver will fail in usually some odd ways. So just be aware that right now we don't have any way of automatically detecting that for you. That might come in the future, but just be careful when you're defining your optimization problem and think about the way that you're setting up your constraints and whether or not they may be redundant. So now that we have our dynamics, our cost function, and our constraints, we're ready to kind of put all that together and define our optimization problem. So we literally just take the problem out of TrajectoryOptimization.jl, pass in our model, objective, initial and final states, our final time, and our constraint set. And with that, we've defined our problem. Then we're also going to provide an initial guess for our controls. Here, we're just going to supply it some like a very small amount of controls, just so it's doing something. This usually allows to break some of the symmetry that you would have if you just like let it sit at 0. And then with that, we have defined our problem, and we're ready to actually solve it and create our solver. And to create the solver also, it's just a one-liner. You just pass the problem to your solver, and then you call solve. Let's go ahead and do that. And you'll see that it took, should have taken just a few more iterations now. Let me just make sure I reevaluate everything and make this up to date. All right. So here it's going to call the solve method. It's taking about 88 iterations, about 200 milliseconds. So not super fast on this particular one. But now let's talk about kind of analyzing the results and looking to see what we're getting out. So we can plot the results pretty easily. We can just use the plots library out of Julia, and we can pass in just by using a function and the times, and pull out the first two states just like this, and we can get those plots very easily. And then also let's do a similar thing for the controls, and then yeah, so then we know what we're looking at, and we have a good idea of what to compare against. And then, all right, now time for like a brief dive onto solver hyperparameters. So as with any kind of nonlinear optimization, it really is going to come down to changing the solver parameters in order to get good performance. So if we look at all the solver parameters or solver options in ALTRO, there is a lot of them. This may look terrible, but in reality, there's only like 5 or 6 that you're going to end up changing on a frequent basis. And I put together this kind of one of the purposes of this example is to show you that which ones to change, and then also provide some key insights as to what to change and why. All right, so let's go ahead and, so as far as kind of the convergence analysis, or kind of controlling how coarse a solution that you want, there's just a handful of tolerances that you need to worry about. So one is the cost tolerance. So this determines what the kind of a minimal amount of change between iterations that you want to, as far as your cost goes. Usually that one gets satisfied fairly easily. And then the constraint tolerance is how much constraint violation you want to satisfy. And this gradient one is usually a little tricky with iLQR or DDP, but we kind of don't play around with that one too much. If you really want to like drive down and really get tight optimality conditions, you can drive down the gradient tolerance, and it'll force the solve to get very, very tight tolerances there. But usually we don't care honestly that much about the cost when we're solving robotics problems, because the cost is fairly arbitrary. It doesn't exactly measure what we care about. So we can analyze, we can pull out the tolerances that we're using right here, and we can change all of these options in a few different ways. So we can either do that when we pass in when we create the solver as keyword arguments, or we can do it with the set options command, or we can set them directly in the solver. All right, so easy, all of that you can change, and if we change that, then you'll see that it took maybe like one less iteration, because this is really just changing what's happening at the end. What we really want to do is be able to change like how it's converging through the process of the solve and all of the internal iterations. So here you can see that it originally took 88, and now it's just taking 87 iterations. And you'll see that the max violation isn't as tight because we relaxed the tolerance. Also, we provide this kind of convenient function for finding where the maximum violation is occurring. If you're curious where it wants to, where kind of that maximum violation is happening. So here you can just use the find max, and it'll tell you that it's happening at the goal constraint at the second index. So very useful for debugging when trying to get a problem working. All right, so now let's actually really improve the solve. So underneath the hood, it's using augmented Lagrangian with iLQR. So I think all of the solvers that we've seen today are using DDP or definitely use DDP as a main part of the algorithm. And that's because it's fast and it works super well. And we, in order to handle constraints, also use augmented Lagrangian. I think we were maybe the first between all three of these solvers to use augmented Lagrangian. But it works in practice just very well and pairs very nicely with DDP and iLQR as was previously mentioned. And in order to kind of dial in the performance, there's really just a couple dials that you need to worry about. One is kind of the intermediate tolerance for the DDP or iLQR iterations. So if you allow them to kind of kick out early, you take more outer loop iterations and you update your dual variables faster, which can in many circumstances help you out. So you usually dial just leave it at the default at the beginning, but then you can relax that when you're trying to dial in the performance for your problem. The other two key ones are the penalties. So augmented Lagrangian is essentially a penalty-based method with some extra tricks for approximating your dual variables. And so modifying the way that it's or how frequently those penalty parameters are updated and how much they're updated and how much penalty parameters you start off with can dramatically change the convergence of your algorithm and how fast it can converge. So generally, if the unconstrained problem is a good initial guess for your constrained problem, then initialize your problem with a low initial penalty. So this will essentially put all of the penalties to very, very low parameters, and they'll solve the unconstrained version. And then they'll use that and slowly bump up your penalties. And so you'll be using the unconstrained solution as a good initial guess. Sometimes that's not what you want. Sometimes you want to maintain feasibility. And so having a good high initial penalty will help you achieve that. And then generally for the scaling, you want to keep that between 100 or 10 to 100. And really only dial that in as the last piece. And if we change this for our Cartpole, you'll see that it took 88 iterations before, and now it's only taking 40. So we half the number of iterations by just tweaking some of these solver parameters. And this is all with the original number of or tolerances, solver tolerances. So you can come back and look at these. I've kind of summarized these in writing here that you can take a look at. This is all also documented in the documentation for ALTRO and for TrajectoryOptimization.jl. They all have their individual documentation pages. And to highlight some of the visualization features that we have, so we can pull in that TrajectoryOptimization package that I mentioned, along with the robot zoo that has the visualization defined for you. So here we can boot up a visualizer right in our Jupyter notebook. You can also open it in your web browser. It's a web-based visualizer. And we just pass our trajectory, and voila, there's our animated trajectory. So very easy. You can also, if you want to, this doesn't look super great on the Cartpole, but you can plot the intermediate waypoints. So here you can do just a couple, pass which time indices you want to get, or you can pass the number. And so that'll give you something nice to generate something for your publications if that's what you need. And we can go ahead and clear those out. And another nice feature is that we have kind of baked into the visualization package is if we want to compare two different solves or two different trajectories, we can do that kind of very easily. So let's say we wanted to change the mass and solve a new problem, and then see how that affected the final trajectory in the visualizer. So we're going to go ahead, just modify the mass, create a new problem and a new solver, and then solve that one. Does that very quickly. And we're going to go ahead and create a new visualizer. And then to visualize it, all you do is you pass in the two trajectories with the model out of Robot Zoo, and we can also change the color. And there we go. And we're now visualizing both of those together. So hopefully this is a decent high-level overview of how to kind of go through all of the steps of setting up and solving a basic trajectory optimization problem. So I'm just going to go very quickly over one other of the examples. Well, I'm just going to do the quadrotor. I'm going to go through this fairly quickly because we only have a couple minutes left because I want to open up some time for Q&A for those that like to open it up for Q&A. All right, so as I mentioned, trajectory optimization and ALTRO kind of natively handle the space of 3D rotation. So this example will kind of highlight some of that. So we're going to start off by defining our dynamics. So rigid or robot dynamics automatic already has a lot of methods baked in for handling single rigid bodies and some multi-body systems. So here, all we need to do is we need to inherit from the robot dynamics rigid body class. And this is parameterized similar to using like a template parameter in C++ on the rotation type. So this rotation could be Euler angles, it could be a modified Rodriguez parameter, or unit quaternions. By default, we're just going to use unit quaternions because they're globally non-singular, and they only use 4 parameters. So we're going to go ahead and create our quadrotor with all of our inertia information and the and models for our actuators. And here, all we need to do is define the control dimension, since the state dimension is going to be defined implicitly from our rotation representation. It's going to be either 12 or 13. And then we can define the constructor, just fill that out, don't worry about that. And then here, we're going to define our forces and our moments acting on our rigid body. So this is a very, very general way of defining single rigid bodies system. So just given the state and the control, what are the forces and moments that are acting on whatever my system is? So you can use this for aerospace models, for underwater vehicles, or for systems up in space. So we've used this a lot in our lab to model everything from quadrotors to Mars entry vehicles. So here, we just define those, and we define the mass and the inertia for our system, which are just pulling directly out of our model, and that's it. And it takes care of all of the, there's also methods in there if you look at the documentation for converting things between the body frame and the world frame, and a handful of other kind of convenience methods for working with these types of systems. So we're going to go ahead and create our model and test it out, make sure that our dynamics are working right. So if we pass in level flight, we should get a next dot of 0, which we have. All right, and we're going to define a cost function. So here for this problem, we're going to be designing like a zigzag trajectory. So we're just going to do something a little bit more complicated than we saw before. Again, we're just going to go fairly quickly through this. The details aren't really important, but you can use all the methods that we saw before to create our objective, which is basically just a vector of all of our individual cost functions. And then we're going to add in a simple bound constraint on our controls to keep them from going negative. And we're going to set up and solve our optimization problem. Sorry, I forgot to mention something on the cost function. So our normal quadratic cost function is going to be doing something like penalizing x minus x ref, which for a rigid body system is not kind of well defined. Just naive subtraction between, for example, two quaternions doesn't accurately capture what we're trying to do. So in order to kind of do that accurately, TrajectoryOptimization.jl provides this quaternion LQR cost, which penalizes a geodesic distance between quaternions, which ends up being very nice and is actually linear in those parameters. So just if you're working with that, just go ahead and use the quaternion LQR cost. And we can boot up our visualization as before and go ahead and visualize that. you'll see here that we get out the trajectory. And then, so continuing on, again, I'm just going to do this. Basically, if you continue on, it'll show you how to set up an MPC problem using this and kind of how to track it with the gains that are stored in the iLQR solver. So that's kind of all the detail that I wanted to go into for the live session. So at this point, I'd love to open it up for questions on ALTRO, and then also if you have additional questions, that's kind of like the last installment of the tutorial part of this workshop. Feel free to ask questions both about ALTRO and to Farbode and to Nicholas about their solvers as well. If you have any residual questions that you'd like to ask.
Okay, thanks a lot, Brian. Now, as before, everyone, please either raise your hand or ask your question directly in the console.
So while we're waiting, maybe I can do a little shameless self-promotion and just ask you, you mentioned some of the second order cone stuff in our package. Could you just either like show that off real quick or explain where it's useful and like what it's actually doing? Yeah.
Yeah, so we have the Rocket NPC example here that you can walk through. And one of the, like, for those of you who are familiar with like the Rocket soft landing problem, this is basically setting up a linearized version of that. And here we can set up our the thrust constraint that needs to be within the second order cone. It's really just as easy as passing the second order cone to our constraint. So underneath the hood, this is just using the augmented Lagrangian method to project the dual variables into to be dual cone feasible, and then it's differentiating through that projection operator as part of the penalty term in the cost function. So all of that is basically transparent to the user, and we've done some benchmarking on this and compared it to state-of-the-art conic solvers like Mosaic or ECOS, and we're at least one order, usually about 2 orders of magnitude faster than those solvers. So we've shown that this works really, really well for SOCPs, and we're looking at adding additional types of conic constraints as well.
Also useful for friction codes.
Maybe I can ask the next question. So could you talk about a little bit the ROS interfaces? For example, in robotics, many groups or many control pipelines are based on ROS. If someone wants to interface this solver with the ROS, how he can do that?
Yeah, that's a good question. Right now, we don't have any like direct ROS kind of interface. There is a ROS interface in Julia that you can use. We in our lab haven't done much. We actually don't use ROS. I don't think we've used it at all yet. So there hasn't been any like need on our end to do it. But it definitely is possible. But yeah, we currently don't have a ROS interface.
Jaskaran?
Right. Hi. Thank you. Thank you for the tutorial. So I got 2 questions. First one is in the tutorial you mentioned that your inequality constraints have to have control. So you had g of x k u k less than equals to 0. Is it explicitly required that the control be there in those constraints? Can you have pure state inequality constraints?
Yeah, absolutely. Yeah, it's just the general form. You like. Yeah, you can have one of just controls or just states, and you can actually specify that when you create the constraint and when you define it yourself. Actually, I have it right here. So here, you can inherit either from stage constraint, which is saying either both, or you can inherit from state constraint or control constraint, and it'll specialize the sparsity of the Jacobians for to leverage that information.
Right. And so I had another question, which is that, is it possible to get co-states as well?
By co-state, you mean the dual variables, the Lagrange multipliers?
No. So the ones that you get from the minimum principle.
Yeah. So we still have the discretized version, and believe if I have my optimal control theory right, those end up in the discretized version just being the dual variables for your dynamics constraints.
Yeah, they're the gradient of the cost to go, right?
Yeah.
Which we do, yeah. They're not, they'll be discretized using whatever integration method you choose when you set the problem up, but they're there, yeah. And you have access to them if you want.
Yeah, yeah. You also have access to, as I mentioned, the ALQR gains.